Hello students, my name is Shashank Shekhar. So we have started the chapter that is chemical kinetics, and we have seen the rate law, and then we have seen what is order and molecularity. So today is the fifth day of this chapter. So if you look at the syllabus, so we have covered up till this part, that is specific rate constant, rate law and specific rate constant. So this part was covered. Now we will talk today about this integrated rate equation, and especially only for zero order reaction. So we will talk about this zero order reaction. Now I want to make assure that you must remember the previous formulas, the one which I taught about in the rate law thing, the differential rate law. Okay, so you must remember that we will use that formula only for this finding the integrated rate equation. So with this, I would start my chapter. So these are the topics that are to be covered for under zero order reaction. First of all, I will give you a general algorithm. So with the help of this algorithm, you can find this integrated rate law for any order reaction. Say we have a zero order or we have a first order or second order. So for following this simple algorithm, you can find it for any order reaction. So we will apply the same for the zero order reaction, and we will see first of all what is zero order reaction. Although we have seen it, but we will see in much more detail. Look at the graphs of it related to that zero order reaction. Then we will try to derive the integrated rate law, and we can derive it in another way also. That is the alternative way we will see. Then we will see the relative graphs to it. So I want to make sure that you are clear about the graphs. Okay, so you must be very clear about the graphs in this chapter, and you must know what are the equations of the graph, like our simple equation that is equals to y is equals to mx plus c. That is the graph for our, say, this straight line. And not in this lecture, but in the next lecture, you will see the exponential graph also. So you must know this graphs. These two graphs at least you must be remembering, because they will be used to and fro throughout these lectures. And graph is important because questions are asked from there. You must be given a graph. You have to calculate the slope and something like that, so that you can get the idea about the order. So I would make certain ways, or you can say I will suggest certain ways in which you will be able to find the order of reaction. And in that, plotting a graph would be a major way. The question will be mainly asked from that part only. I would suggest that you should know the graphical representation of various equations. At last, we will see the example of zero order reaction. So we'll see one example of zero order reaction. So it is very important to see how this things works. After completing this, if we have good enough with this time, then we would see just an introductory part of this first order reaction, because I have just introduced the algorithm. So we will try to use this algorithm to find it for first order reaction. There would not be slides. There would be just some instructions to do so. So if I talk about the algorithm, so first of all, you will write the differential form of the rate law. For this, you must know the order. Okay, so if you are not aware about the order of the reaction, you cannot do this. So first of all, you must know the order of the reaction, and knowing the order of the reaction with respect to different reactants, not the overall order, but the order with respect to different reactants. And if only one reactant is present, then with respect to that reactant, or you can say overall order. Therefore, first of all, you will write the differential form of the rate law. After that, you will rearrange the equation so that such that the one with the same coefficient are on the same side. Likewise, if we have dx on one side, then all the terms which are related to x, okay, like if I have x square or x cube, so all things like that should be on the dx side. And on the other side, suppose we have dy, then all the terms related to dy would be on the dy side. So this should be kept in mind, okay, that you should first of all rearrange the equation such that you can integrate it properly, because our main purpose is to find the integrated rate law from the differential one. Now, when we rearrange the equation and get our coefficient on the better side, then we integrate it. Now we have two ways to further proceed. First way is, if you are aware about putting limits, then first of all put the limits and then integrate. So this is one way. And you can do it after integrating also. You do it after integrating, then take it at times t is equals to 0 and time t is equals to t1, put the value, you can also get that thing. So I will show you both the ways, you can follow either of them. And why it is important to derive such things, because you will see in some case, or you will be given in exams also, you will given equations, and that equation will not be the general equation. For that you have to integrate, or you can say you have to follow the whole algorithm, and then only you will be able to find this integrated rate law. So once you integrate both sides, put the proper limits, then you will get the final equation. So I want to make sure and that you learn it for basically zero order and first order, because that is only mentioned in the syllabus. So we will see for zero order and first order the integrated rate law. Now let us first start with the zero order reaction. So first of all, what is a zero order reaction? It means, what does it means? That the rate of the reaction is proportional to 0 power of the concentration of reactants, which would be written as, suppose R is going to P, where R is the reactant and P is the product. So if you write the differential rate law in terms of reactant, one more thing that should be added in our algorithm is that you should write the differential rate law always in the form of reactant. In the form of reactant means the rate law should be expressed in the terms of reactant. You cannot use this equation, that is dp by dt is equals to kr. You cannot use it like this, because when you will try to rearrange the coefficient, you will not get the terms related to p, and that would create a problem because you will not be able to integrate it. Okay, and in most of the time we are well aware before the reaction about the reactant concentration. Product concentration, to find the product concentration, it takes bit of a time. So we deal with this reactant only, and if you want to integrate and get the integrated rate law, then you must have this in terms of the reactant. So this should be kept in mind, that you will not use this equation because you cannot rearrange the coefficient to integrate it further. So we will write always in terms of this reactant. So I have written here dr by dt, that is rate of disappearance of this reactant along with a negative sign. So this whole makes up the rate of disappearance of R. Now we have made it clear that it is a zero order reaction, so that will be equals to the rate constant K multiplied by the reactant raised to the power 0. So I have told you earlier, since this is a zero order reaction, so the concentration will be raised to the power 0 power. So this is our differential rate law. Now what can you primarily derive from this equation? Now if I draw a graph that is rate against time or concentration, both, rate against time or concentration, okay, then what will happen? This rate will remain constant, because why I'm saying that we can write time and concentration both, because suppose with time what does increases. So concentration of product, you can write product, or you can say reactant also. So what I basically mean here is that with respect to time, the concentration will decrease. Okay, with respect to time, concentration will decrease, but still, since this rate is independent of concentration of reactant, we can not see any change in this rate. It remains constant. Okay, so with time, with passage of time, this concentration decreases, but it has no effect on the rate. So this is the first thing. We can just plot it against reactant also. So what we will do, we will not take one reaction, we will try to conduct several reactions. Suppose we take 5 sets of reaction, in all of which we have different initial concentration, and then we plotted, then we got the rate, instantaneous rate at that point, and plotted all of this as point like this, here, here, here. Suppose we have done first reaction and the instantaneous rate of reaction at that point was R1. Then we did the second reaction at suppose that point was R2, and it is R3, it is R4, R5 and R6. Suppose we have done 6 sets of reaction taking different initial concentration, and then we have calculated, or you can say evaluated this instantaneous rate of reaction, initial instantaneous rate of reaction at same time. Then we will see that the rate will remain constant for all of this. Okay, so all of these plots will be on a linear plot. Okay, so instead of this we can also take initial rate, initial concentration, or we can take it for one reaction also, in which we are seeing the rate against time, since and with the passage of time the concentration of reactant decreases, but it has no effect on rate, so it will also give you a straight line with a zero slope. Okay, so this is clear. So if you compare it with the equation of line, that is y is equals to mx plus c. So you can see here that this thing, this is the thing, it has a zero intercept. Okay, so c is equals to 0. Sorry, m is equals to 0, mx is equals to 0, because c is always a constant and this is a constant. Okay, so c is equals to k here, c is equals to k here. That's why we got something which is constant like this, and this mx is turning to 0. So this is the plot. Now you can be also given this equation, rate is equals to, say we have k r naught. So this equation will also give you the same graph. It is the same equation, only we have put the differential rate form here. So this was all about zero order reaction. Next we have the integrated rate law derivation. So this is the main part of this lecture. So what we will do, we will take our, say, this thing, that is the differential rate law, follow the algorithm, take the limits, first of all rearrange the coefficient, integrate it, take the limits, put it there, and get our final equation. Suppose we have a zero order reaction like this. This is our zero order reaction. Then the rate law would be simply, we have seen it earlier also, it is rate is equals to minus dr by dt, that is rate of disappearance of reactant, is equals to kr to the power 0, where k is the rate constant and r is the reactant concentration raised to the power 0. Now we know it well enough that something raised to the power 0 gives us 1. So it happens here also, and we get rate is equals to minus dr by dt is equals to k. Okay, we get rate is equals to minus dr by dt is equals to k. Now what we are doing, we are just, say, rearranging the coefficient. So we put this dt along with k here. So this will be done always. So if I try to just put a mnemonic device here, or you can say a shortcut here, then you should remember that the dt should be always on the k side. Okay, as any quantity is raised to the power is unity, so therefore it would give us this. Okay, the same thing is written. Okay, next, now we'll integrate it. What we have done, we have integrated it. So we have this equation, sorry for not mentioning it here. So it was like this, and k dt. So what we have done, we have integrated it. So this dr would give us r, it would have a negative sign, and since we are not doing an under limit, so we will have a constant. Therefore it would give us k dt. So k is again constant, it will go outside the integration, and dt integration will give you t plus c. The whole of the equation will become kt minus c is equals to r. Now you will say that why it is not written, suppose the constant is I here, why it is not written minus. Okay, so we have this thing, we'll have this. Okay, so you must be saying that why are we not introduced with minus I, and why it is written plus I. So if you are imagining a constant, it can be minus I and plus I both. Suppose we write it as this. Suppose we initially assume that this is C, and we can write it like this. Okay. Now this thing is here is taken as constant, that is minus C is taken as I. So I is the constant of integration. So is this clear to you? So this method right now which I am saying would not be that much easier to follow, but if you take the limit one, so I will tell you in the next slide. If you take the limit method, then it would be more appropriate. Okay, so you can use that limit and you can find it in ones. You do not have to follow a second or third part, which I will be following right now. So what we have to do is we have to take at t equal to 0. We have to take a time t equal to 0. So at that time, at t is equals to 0, that equation turns into r is equals to plus I, and this I is taken as r naught. So what I am saying here, suppose this r, we are getting it as I. So what does it mean? So at time t is equals to 0, the r, this is the concentration, will be equals to initial concentration. Okay, so it is clear. So this r at time t is equals to 0 will equals to initial concentration, and since here r is equals to I, therefore I is equals to r naught, which is the initial concentration. So I have just plugged this value at initial concentration, I is equals to r naught here. Okay, now we put this value back into this equation which I have here, that is r naught is equals to minus k ti. Okay, therefore substituting this value, we got it as this thing. Okay, once again we know that at time t is equals to 0, the concentration of r will be r naught. We have assumed that the initial concentration is r naught. Then what we have done, we have substituted t is equals to 0 here and try to find r from here also. So basically what I mean, so first we have assumed the initial concentration of reactant r, that will be equals to r naught, and then we try to find this r naught from this equation. So we know time t is equals to 0, r is equals to r naught, therefore r naught is equals to I. So we found the value of I, we put it back here, and we got our final equation. So this is important equation, you should remember this. We can write it in this way also if you want, that k is equals to r naught minus r by t. You can remember this also, it's your call, but I would suggest that you should remember this one. Okay, sorry, this one, because this would be helpful in your graphs also. Plus it will be helpful to calculate the concentration at time t in one go. It's your choice, it's very easy to go from here to here or either here to here, so you can remember any of these. Instead, I would suggest that you should also kind of remember this integration, because it is important. It can be it can be asked, or it is asked in the exam also sometimes, that derive the first order or the zero order or something like that. And if you remember this, it would be easy for you, okay, for doing it for any of this order. Now suppose what happens, what do we do is we take something coefficient in this. Okay, what do we take? Something coefficient in this. So suppose we are going from r to p, we say that it has a coefficient n. Then in that case, the rate will be equals to 1 by n dr by dt, and we have this, say we have this k. Okay, we will have this. Now if you integrate this one, that is dr minus 1 by n is equals to k dt, finally you will get here r by n, where n is the coefficient. So that would give you the formal final formula as r by n is equals to minus kt plus r naught. Okay, So see why you should remember this coefficient, this integration, because sometimes you can be given a coefficient. So if you remember the initial equation, that was r was giving p directly. We have no this coefficient instead of here. Okay, so that's why you should remember this algorithm. So if you are suppose introduced a coefficient, then the whole procedure will change in a minute manner, but that would affect your answer in a major manner. Okay, so that would give you a completely different value, because the concentration at time t would be now equals to n times this equation. Okay, n times this equation. So this is important, right? Now if I move to the next way of finding the integrated rate law with using limits. So what we have done, we have again taken that same equation. Here I have just removed with r with a, no problem. Take it as a going to b. This is just a generalization. Now what we have done, during integration we have taken limit. We are saying that at time t is equals to 0, we have this concentration, that is a naught, and at time t is equals to 1, or say at time t equal to t, we have this concentration at. So this is related to this, and this one is related to this one. Now we are integrating this thing. Now we will see that how easily we are integrating and getting our final answer. So this integration would give us this one, a, and the limits are a naught to at. Similarly, this dt integration would give you t from 0 to t. Okay, now a starting from a naught to at, therefore a naught minus at minus a naught, this is because this is the final one. At minus a naught is equals to t minus 0. That would give us finally t, and this is at minus a naught. So if you rearrange this equation, then we will get this thing. Okay, now here we have a negative sign. Sorry for not introducing this one, because we are dealing with reactant, so of course we will have a negative sign at the start. Okay, so if you just introduce this negative sign inside, you will get it as a naught minus at is equals to kt. So that would finally give us k is equals to a naught minus at by t. Okay, so this is our same equation. We got the same equation, but what we have changed, we have introduced limit here. Remember this one. So we have a 7. Okay. So what we have done is we have left this negative sign. Sorry for negative sign. That would give us finally this. So this is the equation. Now let us try to plot a graph. So our final equation is this one. So we will use this equation and try to plot our graph. So what we have done, we have compared it with the standard equation, that is y is equals to mx plus c. Okay, y is equals to mx plus c. This is our standard equation, straight line equation for a straight line. Now if you compare both of these equations, now children do get confused that why we have taken y as this one and not this one. Okay, so first of all I want to make a point clear that this y is a kind of variable, it should be changing, and c is a kind of constant. So this is constant, you know it very well. So if you know the straight line equation, you know it, that this is constant. Now this r naught here is also a constant, because once whatever you have taken the initial concentration, once you have taken, it is taken. With time it will not change at all, because that is a fixed thing. Now if I take this y here, then it will not change at all. Okay, so you will see a straight line. This r naught is of course not a variable here. So that's why what do? We take this as constant, not as y. So if you compare both of these equations, then you will get slope is equals to minus k, that is m is equals to minus k. So y is equals to minus k. If you compare it with the equation, we have a plus sign here, we have a plus sign here. But you see m, if you compare this, then this minus is not present in this equation. So children do make mistake here, they do not include this minus. So it is with the minus sign. Therefore slope is equals to minus k. So we got a something that is having a negative slope. Now you will say, how sir, how did you decide that k will have a negative, not a negative value, but always a positive value? So if you remember the rate law, it goes like this: rate is equals to k a to the power n. Now suppose we have taken the concentration as 1. So that would give us rate is equals to k. So k is a kind of specific rate constant. Specific rate. Okay. And you know it very well that this rate can never be negative. Okay. So for this reason, this k will be always positive because it is a rate only, but at concentration is equals to unity. So at unity concentration, this is equals to rate only. Okay, so that for that reason, we always take it as positive. So positive with a negative would give us a negative slope. At x, we have this, that is time. Okay, and this is c. Now you will again ask that why do not we take this k, that is the rate constant, as x? So here also you can see that the slope should remain constant for a given graph. And you know it very well that k is the only constant in both of this. Time will change, of course, and rate constant will remain constant. So, and since slope should also be constant, therefore we have taken m is equals to minus k and not minus t. Okay. So this is the equation. And y-axis we have the concentration at time t. Okay. So at y-axis we have the concentration at time t, that is 80. Now we plot the graph. Sorry for this. It would not be here. So this would not be here. Okay. This is wrong because we cannot take negative time. Okay. So this is our thing. We got this graph. So you can see that we have a slope intercept. So this intercept is equals to c. So one more line I should add here, that we have a intercept is equals to r naught. So the intercept is equals to r naught or a naught, initial concentration, whatever it is. So this is our intercept. At y-axis we have our concentration at time t, and we have at x-axis time, this t is moving, and this slope is along with a negative sign. Okay, so we will have a negative slope here. So this will go down and down. So this is the graph for zero order reaction. Is this clear? Okay. So we have this graph. So these two graphs are very important. First of all, the rate against time or the rate against different initial concentration, both will have a parallel line with the x-axis. And for this zero order reaction, for the integrated rate law, we can have this graph which has a negative slope, okay, and has an intercept of is equals to that is equals to initial concentration. So we are done with the quantitative, you can say, approach of this zero order graph. Now let us see an example of this. Let's see an example of this. So zero order reaction are not common. First order are most common one. You will see the first order and the second order also. Many times you will see the first order and many times you will see the second order. But zero order is not that much common. But there are some reaction like the enzyme catalyzed reaction which occurs, and the reaction which occurs on metal surfaces. So they are some of the few examples of this zero order reaction. So you can imagine why it is on the reactions on the metal surface is zero order, because so metal is just acting as a catalyst and it helps in decomposition of that given gas or liquid, that primarily liquid and gas and sometimes solid. Okay, so since we are decomposing this single entity into several components, so there will be no collision. Okay, and due to this reason we have a zero order reaction in which the reactant itself breaks into products. So the very famous example is this decomposition of ammonia on the platinum catalyst at 1130 Kelvin. So very high temperature is given so that it can decompose. So it decomposes into nitrogen and hydrogen gas. So if you we try to write the rate law, that would look like this. That is, rate is equals to K NH3 raised to the power 0 is equals to K. Now if I ask you, what did you get from this equation, rate equation? So you will primarily say that okay, we got that we have a zero order reaction. And second, you can say in a way that this equation that is given, it is not an elementary reaction. Not an elementary reaction. How? Because if it would have been a elementary reaction, that the coefficient that is present here 2 would be the power of this, say this NH3, and the rate will give us K NH3 raised to the power 2, and therefore the overall order will be second order reaction. But we see that we have a power of 0. This means that this is not an equation for the elementary reaction. So this is a you can say complex reaction mechanism. Okay. Now in this reaction, the platinum acts as a catalyst and not as a reactant, and at high pressure the metal surface gets saturated with gas molecule. So a further change in reaction condition is unable to alter the amount of ammonia on the surface of the catalyst, making the rate of reaction independent of its concentration. So what does it mean? So a further change in the reaction condition is unable to alter the amount of ammonia on the surface of the catalyst, making rate of the reaction independent of its concentration. Now, this statement says that we cannot change the rate of reaction if we change the concentration of this ammonia gas. Okay, so we have find from the experimental data that changing the concentration of ammonia has no effect on its rate. Similarly, we have another example in which we have again a thermal decomposition of a gas, that is Hi, on gold surface. So this is also an example of zero order reaction. So you can see that what type of reaction can undergo the zero order, in which it mainly includes the decomposition reaction. Because to transform something into something, just simple transformation will require a, you can say, external entity in general case. And since you can predict that if it is a decomposition reaction, then it may be a zero order reaction. I will not suggest to just blindly follow it. It is just a kind of, you can say, a knowledge type thing. It will not be asked in your exam. It suggests the rate of reaction or suggests order of reaction without any experimental backup. So you will be given experimental data, and on that basis only you will be asked to say that whether it is zero order or first order. So that is clear. Or either you can be given the chemical equation along with that it is a elementary reaction, then and then only you will be able to find the rate of reaction and order of reaction both. Okay, so this was all about the zero order reaction. Now I have told you earlier that if we are good with time, then we will see something about the first order. So I'm just giving you a work to do by yourself. It is a good practice to do, so you know that what algorithm should we follow to find the integrated rate law. So I have done it for zero order reaction. Try it for the first order. So I'm giving you the start. So first of all, write the differential rate. Very easy to write differential rate form, and we are assuming that only we have a single product with a coefficient of 1, of course, that is going to a product B, and it is given that is a first order reaction. First order reaction. So that would give us minus dr by dt Ka to the power 1. So first of all, what you will do? You will integrate it within limits. First of all, you find the or write the order. Then you will write the differential rate form, integrate it within proper limits, and then you will get your final equation. So the limits would be at initial concentration, you will have this R0, and the final concentration you will have RT. You will also rearrange the coefficient. So that coefficient would look like this. This is R. Okay. Suppose R is going to be. Right. Then we will have this dr by R K dt from time t is equals to 0 to t is equals to t. Integrated within limits, you will get your equation. Try to get it. Try to plot the graphs also. So this can you can do it as an assignment. In the next class, we will see that what is the final equation. So this was for today's class. Thank you.